Hey guys, welcome back. We're going to move on and talk about type 1 and type 2 error. We actually already know type 1 error. That's called a false positive. We've been talking about that. That's whatever you set the alpha level to. So there's really only one new type of error we have, which is a type 2 error. And if a false positive is a type 1 error, a false negative is a type 2 error, which is also related to the power of the test and the effect size as well, which we'll get into in more depth tomorrow. But I've got a really cool visual that I want to show you guys, and a kind of a funny example that's from the book as well. So speaking about the book, lots of good stuff in there. That's how I learned stats. So if you want to be as good as I am in stats, read the book and get a degree in math. But hey, whatever. All right, so pages 524 through 528. So the next 4 pages are what we're going to be covering today. So I'm going to try to bring those pages to life to you, hopefully with the visuals and the images that are interactive. It's pretty epic, a lot better than a textbook, if you ask my opinion, and some fun conversation as we go. So we are talking about human touch therapy, and I actually Googled it, and it's a thing. It's not just massaging, but it is a medical field of where you can sense and manipulate human energy fields with your hands. If it sounds like chakras or acupuncture or something like that, it's very similar. All right, so is it real? And I should be more fair, but is it real? Let's investigate it. So can you heal somebody by manipulating the human energy field by touch? Good question. Let's find out. All right, so I should know this one. I think you can look at the book. I think she was in 7th grade. Maybe she's younger. Anyway, she decided she would conduct an experiment. And so she took this licensed human touch therapy expert who claims that they can sense human touch. So if you put your hand over their hand, they can sense the magical field of the waves being manipulated, and they can sense your touch, right? So she put her behind a 50-cent trifold with cuts out of it, and she hovered her hand over either her left hand or her right hand, and she asked the human touch therapist which hand she was hovering over. And so the question is, can they sense the human energy field? So is there something to it? It's like, is it a biased coin, right? So if it's not a biased coin, we would expect 50-50, right? If she can't sense it at all, if she has no ability to sense the human energy field as your hand hovers over hers, then we would expect that she would get this right 50% of the time, right? But if she could sense the human energy field, we would expect more than 50% of the time that she would be able to detect the human touch not the human touch, but the human energy field that is hovering and interrupting her human energy field as she manipulates it and causes healing. Okay, so a bunch of anyway, moving on. This is kind of fun. I enjoy this because it's fun, whatever. All right, so our null hypothesis is that she can't detect the human energy field. So it's innocent to proven guilty. It's a fair coin until we can prove that it's not, right? It's no better than just random chance of 50-50 until we can prove the burden is on her to be able to prove that she actually can sense the human energy field. So our probability is going to be 50%. Our null hypothesis is 50%, which means that there was no difference in random chance. She can't detect anything. It's just pure random chance. Then the alternative is going to be that the proportion is going to be greater than 50%, which would mean that she was able to detect more than half the time she was able to detect the human energy field. Now, you would think, okay, what percent of the time would you really want her to be able to detect it? Even if she was able to detect it 55%, and even if we did a large enough sample size, that could be statistically significant, a 5% increase. But would you shell out, thousands of dollars for this human energy treatment? And I looked it up. There actually is a place in Texas, I forget where in Texas, and there was one review, and it was a 1-star review on Google. So I don't know. Maybe they'll go out of business single-handedly because a 7th grader called them out on their BS. Okay, you should ask me what I think about what are they? Mediums or psychics. It's the word bull. Oh, I'm gonna bleep that out. Anyway, watch me forget to. All right. Anyway, so our null hypothesis is 50%. Our alternative hypothesis is that it's more than 50%. Now, we would, of course, want to create a confidence interval to see what we think the actual true proportion is, and clearly it has to be more than 50%. And then the next question is, even though it is potentially statistically significant, is it practically significant? So is it enough of a if it's high enough above 50% that we believe that it's worth spending thousands of dollars, that this is actually like a legit field. But hey, people spend their money on what they spend their money on. All right, so next thing we want to do before we calculate a p-value or do any sampling, we want to select an alpha level so that we're not being accused of fine-tuning our alpha level to fit our predetermined deposition against it, which obviously I have one, but I also know how this whole thing is. Okay, so choose an alpha level. On this one, we might default to 5%. It's obviously more important than a sloppy alpha of 10% because, I mean, I would say that. It's not as strict as burden of proof of 1% like what we would say with beyond reasonable doubt with somebody serving a life sentence or something like that. All right, so this would be whatever we set our alpha level to is the probability of type 1 error. So that's a probability that our null hypothesis was actually true, that it actually was 50%. I suppose I should update that. You get the idea. That it actually was 50%. We just failed to detect it. So that would be the probability of type 1 error. Now, if we get a sample proportion that's in the top 5%, that can still happen by natural random sampling variation with a true null hypothesis of 50-50 5% of the time. So maybe we would accidentally say, hey, she got this right, and we would say that there is evidence to reject the null hypothesis in favor that, oh, she's actually, able to detect it when she really isn't. So what percent of the time are you okay with that false positive error, that type 1 error, which is what we set our alpha level to? And are we okay with 5% of people that we put on trial for murder going to spending life in prison? Oh, innocent people in prison, we don't like that, right? Are we okay with 10%? Certainly not. 1%, even that is scary, right? Because that could happen to you. What if you were one of the 1% of the time the stars align and just appear like, well, you probably did it, so we put you away for life and you were actually innocent. They make movies about this stuff. Good movies, actually, about it. Shawshank Redemption. You should watch that movie. It's a good one. All right, anyway, so 1%, 5%, or 10%, that's going to be from our sampling variation, 1%, 5%, 10%. That alpha level is directly the exact same as a type 1 error. It's a probability we have a false positive or we reject it even though we shouldn't have, just due to natural sampling variation, even though the null hypothesis is actually true. Okay, so is our sample proportion a statistically significant observation? So she did this experiment 150 times, so a little simulation or experiment or whatever, and 70 of those 150 times the lady was actually able to detect where her hand was. Now, if you look, that is actually less than 50%. So she got it mixed up, apparently. So not only was it less than 50%, and she's claiming that she can sense it, she actually sensed it less than 50%. So this is definitely not trending in the right direction. So the p-value that we get for this is actually going to be higher than 50% because she got it in the wrong direction. Poor lady. And like, this is her job. Like, she's a professional. Oh man, I feel sorry for her. That must have been really embarrassing, like a 7th grader called you out. And that's why I love math, because it's consistent. And I don't look like an idiot. I need to be nicer, and it's like midnight and I got school tomorrow and I'm making this video and I got another video to make, but it's all good. It's all Gucci. All right, so our null hypothesis is 50-50, so it's going to be 0.5 and 0.5. Our sample size was 150. So we start with looking at the true null hypothesis. So if it really is a 50-50, which means she's no better, no able to detect it, this is the sampling distribution model we would expect. Okay, we set our alpha level at 5%. So we set that to 5%. So 5% of the time, we might have detected that she was able to detect it because it was in the top 5%. So we were able to reject the null, which would be a type 1 error because it really was just 50-50. That could happen 5% of the time. Okay, and then now on the bottom, let's say that it's actually, this is from the perspective of our sample proportion. Let's say that it's not. So we start out assuming that it actually is 50-50, right? What if it's actually not 50-50? What if the true proportion was what we got in our sample proportion, which we know that's not actually what it's going to be. It's going to be something else, but let's assume that it actually was less than that. Really, it couldn't be worse than 50-50 unless she got her magic backwards or something. Oh, poor lady, she's got one job and she did it backwards. Anyway, so let's say that that's what it actually was centered at, and then we would look at the probability of these things occurring. So our p hat and q hat, which are based on standard error, which is based on the actual sample proportion. We know it's not the true proportion. That's why it's called standard error, because we know it's just the next best thing we have, because we don't know what the true probability in the long run, the empirical probability. Now, I've got a feeling it'll probably end up evening out to 50% because it's no better than guessing she's full. But I don't know what that true probability is, okay? And so the sample proportion would be the sample proportion that we got, p hat and q hat, okay, divided by the 150, which gives us a very similar standard deviation to what we had here. So those standard deviations are technically slightly different. I don't think I made it where yeah, it was supposed to start over there. You get the idea. So 4.07, very similar to that one. Notice they're slightly different because of the difference in the p hat, the q hat, or the p naught and q naught. Slightly different. Okay, so then the next thing is that if this was actually over here, which is where we actually had it, right about right there, then that observation was not only not in the top 5%, because we're doing a one-sided test. We're only interested if she has the ability to more than half the time, detect the human energy field, right? So not only was she not in the top 5%, the p-value actually would be higher than 50%. So it would be, I don't know, let's put it in the calculator. Let's just do it. All right, so stat, arrow over to test. We're going to go down to a one proportion z-test. And our hypothesized proportion is 50%. The actual number that we were able to get was 70 out of 150, which is less than 50%. We want to know if our proportion is strictly greater than the null hypothesis of 50%. We're only interested if she can detect it more than half the time. And even then, I mean, it would have to be a lot more before I'd spend $1,000 on this stuff. Anyway, and so our z-score is negative. Our p-value is basically 80%. Okay, so more than 50%, certainly not in the top 5%. She was turning in the wrong direction, okay? So, poor lady. So embarrassing. Still can't get over it. There's a sample proportion, and we're good to go. So what do? We reject we do not have enough evidence to reject the null hypothesis, so we fail to reject. All right, and that's pretty much all I've got to say about that. I'm going to show you the next part, which is the part of probability of having a type 2 error, and also the power of the test on the next slide. Okay, so let's say that the null hypothesis is actually true and the hypothesized proportion is true. Then if we get a sample that's in this top 5% or whatever we set the alpha level to, that is our probability of type 1 error. Now let's say that the null hypothesis is not true and that the true proportion is centered at some true proportion, which is just something that's not the null hypothesis. Let's say it's this value p. Okay, and again, we're just sampling to try to figure out what that is. But if we do all of our samples, thousands of samples, it will eventually fill in this true proportion, this sampling distribution model, instead of filling in this one. If the null hypothesis is true, we're going to fill in this one, right, centered at p naught. But if it's not true, it'll be centered at the true proportion, which is here. Now, at this significance level, whatever this significance level was here, anything that's to the right of that, we would successfully be able to reject the null hypothesis, right? And that's not going to happen alpha percent 5% of the time. That's going to happen whatever this area under the curve is, which we call the power of the test, which is the ability of the test with our certain sample size to be able to detect a true change and reject the null hypothesis. So the ability to correctly reject the null hypothesis and to detect a difference, okay? That's the power of the test, which is actually kind of cool, because it makes sense how we use the word and what it means. So essentially, that's this error here. Now, the type 2 error is that, let's say that it actually was different. It's not the null anymore, so we're not looking at the top one, we're looking at the bottom one. But we just so happen to have a sample that varied on the left side that was below this significance level, this significance point here, whatever that proportion was set to be. Then we would have failed to reject. We failed to detect the difference. Now, we can fail to detect it for two reasons, and that's, by the way, called a type 2 error, which type 1 error is a false positive, and a type 2 error is a false negative. So if we think about this in I guess, like testing, so let's say we're doing drug testing or something like that, or COVID testing, hey, how about that, right? So a false positive, which would be the rate that you actually had we thought that you had COVID when you actually didn't have COVID, and that's called a false positive. And by the way, every test has false positives and false negatives. And if you don't ask the doctor what those are, then you're not being a good statistician. So you should always ask, what are the rates for false positives and the rates for false negatives? Then a false negative, which is what we're normally more afraid about, is that you actually had COVID or an STD or whatever you're testing for, and they failed to detect it. That's a false negative. So I could tell you a really cool story. In fact, I will eventually tell you a story, and we're not running long on time, so I will tell you the story. And and I guess I'm going to put this on the internet, but a certain person that I know who had a student in a primary school in a different state, so it's not the state of Oklahoma, so it's not our problem, so I'm not going to give you any more information on that. But anyway, they found a what looked like a white powdery substance, a rock, and this elementary student that I know thought that it was just a rock and stuck it in their mouth because that's what they do when they're in primary school. Well, he got caught having this rock, and they're not supposed to take the rocks from the playground into the school, and so they asked him where he got it from, and he told them it was from home, because if it's from home, then he's allowed to keep it with them because it's his rock, but if you find it on the playground, then you're not allowed to. So that's what he told them. So they find this white powdery substance that he says that he got from home, and they asked him, well, where'd you get it? And he said, well, I guess my dad gave it to me, which sounds bad, right? And so they decided they thought that this rock was a certain white powdery substance, if you know what I mean. And so they did a quick field test. So they called the cops, right? Cops came, they do a quick and cheap field test. And it's a very sloppy test that has a lot of false positives. It's just a preliminary test to see, is it a rock or is it potentially something else that starts with M, rhymes with math but has an E in it, if you catch my drift, okay? And so the preliminary, really rough field test, which has a ton of false positives, like 40% of the time it's a false positive, something ridiculous, like way sloppy. We never have an alpha level of 40%. That's incredibly sloppy, but they did. It's a very cheap test. That's why they do it, okay? Very sensitive test that's able to detect it, but also the trade-off is there's a lot of false positives. That's how this whole system works, right? They thought that it was this certain thing. Wait, I don't even know my drugs. It wouldn't be meth, it would be coke. Whatever, it doesn't matter. Obviously, I don't do drugs, nor should you. And all the people I know who do drugs, like I said before, they're all losers. Okay, so don't do drugs. All right, then they took it to a second test, now that they thought there was a slight evidence that potentially this is crack cocaine or whatever. Then they decided they would do a more thorough test, which costs more money, and they take it to a lab, and then they have to analyze it. And then I believe they determined, I should know how the story ends. Was it actually crack? Was it coke? I don't know. I'll have to ask a certain somebody that I know who also knows a certain somebody who is involved in this in a different state that's not the state of Oklahoma. All right. So basically, they did another test that has a smaller type 1 error, right? So the ability to detect it has lower power to detect it, but it also gives you less type 1 errors. And whatever they concluded, I don't remember. I think they decided that it wasn't actually coke. And so but the whole issue is that they used a really sloppy test that had a 40% false positive, and then they put this family through all this crazy stuff when it actually was just a rock from the playground. And then they questioned this kid, and they put him through all this stress. Child Protective Custodies came out and looked at the house, and like, this is not what a typical house looks like where they do this stuff. And so, because it hadn't caught fire and, stuff like that. We have our own issues in Oklahoma. But anyway, and so all that, and like, could have potentially taken the kids away, which is ridiculous, and that it wasn't handled very well. But anyway, all that to say, whenever you're tested for anything, you should always ask, what's the false positive and false negative rates for this? And every test, no test is perfect. No test is perfect. They all have false positives and false negatives. This feels like a really timely message. You should always ask these questions. And I'm just being honest. All right, so let's look at it from this. Now it moves. This picture is worth 1,000 words. So this picture, the diagram that moves and slides and everything, is worth 100 bajillion words, all right, which is a real number because I do math. All right, so if the null hypothesis is true and it's actually 50%, she has no ability to detect it, whatever we set our alpha level to, 1%, 5%, or 10%, that's going to be the probability of a type 1 error. Okay. Now let's say the null hypothesis is not true, so it's false. There's some other proportion. We don't know what that true proportion is. It's just something different, right? Let's say that she actually was able to detect it, and the true percent of the time she could detect it would be 60% of the time. Let's say that's the true one. So that's about 60% right here. Then anything left of this value here would be a type 2 error. Now it looks with our sample size of 150, we have a pretty powerful test if she actually truly could detect it 60% of the time, which is not even that impressive, right? I wouldn't spend $1,000 for 60% of the time she can heal me or manipulate the energy fields to heal me. Call BS. All right, so that looks like a pretty powerful test. Okay, we would be able to detect it if it was actually 60%. And then a type 2 error would be when we failed to detect it, which would be whenever it was below this significance level, whatever that value was. Okay, let's say that it was just 55% of the time that she could detect it. Well, it looks like 55% of the time is about 10% false positive, and the power of the test is about 50% of the time we would be able to detect it, 50% of the time we wouldn't if the true proportion was 55. Hopefully that makes sense. So as we increase, this is the difference, the offset between the hypothesized proportion and the true proportion. So if we go from 55 to 60%, the offset of that is called the effect size. The greater the effect size, the easier it is to detect it, right? It's easier, obviously, we're going to have a more powerful test. The other trade-off we have is directly a trade-off between the type 1 error and the type 2 error. You see how that moves? Isn't that gorgeous? Like, whoa! I know, absolutely amazing. As we increase the burden of proof, right? As we have a higher burden of proof for our criminal justice system, right? So we are beyond a reasonable doubt. Beyond a reasonable doubt, it's really strict. 5% of innocent people aren't in jail. 1%, right? That's not strict enough. It needs to be like half of 1%. No, half that. No, half that. Put your pinky down. It's a Heat quote reference, but I had to make it. Even the more that we increase the burden of proof, which I get it. My heartstrings are drawn for people who are innocent in jail. But if you ask, all the people in jail are innocent, if you ask them. All right, so then that's what's going to happen is the power of the test, the ability for us to detect and be able to put away violent people who are a danger to society diminishes. So if we had a very sloppy test, right? So like our criminal system, not that, but the civil court, right? The one that found OJ guilty and sued him. And if it just has to be more likely that you did it than not, then we can catch all these people and throw them, lock them all in jail. Rah! And then we catch them all, right? Like Pokemon, gotta catch them all. But then what happens? Our false positive is 50%. It's like 50% of the time that innocent people would be in jail. And that is unacceptable. Even though that you see the trade-offs between the two. There's no perfect thing. But there is one way we can always decrease both types of errors. We can't control the effect size. We can't control how far off this is. Now, if there's a lot of evidence that this person's guilty, like they admitted to it and be like smoking gun, DNA and all that stuff, then the effect size, it might be really easy for us to prove they're guilty, right? They were dumb enough to incriminate themselves and like talk without a law and stuff like that. But anyway, you get it. The effect size, but that's set. We can't control that. What we can control is increasing the sample size. And as we increase the sample size, we decrease the standard deviation on both of these bell curves, which is going to decrease the error on both of them and give us a more powerful test. So the answer in stats is always more data, not just more data, but how we collect the data and is it representative and stuff like that. All right, so I could talk about this till the cows come home, and I'm going to probably talk about it again with the power of the test tomorrow. But I wanted to show you this and kind of wrap your brains around it. Hopefully now it's all starting to piece together and make sense. And it's a beautiful, beautiful, powerful thing. And all this hypothesis testing, power of the test, the effect size, type 1, type 2 error, it's literally all over the place. If you look at all the medical stuff and all the studies and experiments, when is it statistically significant? When do we reject the null? Not reject the null? All sciences, all of it is based on hypothesis testing and inferential statistics. So this is probably the most important part of all the things that I can teach you about stats. It's not probability, unfortunately, even though probability is pretty rad. It's inferential statistics. So I am glad that you have this awesome, legit, like smart board, interactive, like coolness that I get to show you it all on. All right, I'm going to move on. So type 1 error is the error of rejecting a null hypothesis when it was in fact true. It's also called a false positive. That is directly equal to the alpha level. 1%, 5%, 10%. That's the probability that you're setting if the null is true. That one's easy to calculate. The type 2 error is a little bit more difficult to calculate because in fact, it's only possible to calculate the type 2 error and the power of the test if we know the true proportion, which we're trying to estimate the true proportion in the first place. So a lot of this is theoretical. It's not even possible to know the true power of the test or the type 2 error. But in the long run, over and over again, if we're doing like testing for COVID or whatever, we know if the person actually developed symptoms, if they actually had COVID, if we do more testing. So we can figure out what the true proportion is and what the type 1 and type 2 error is. It just takes a lot of time and lots of studies and stuff. All right, type 2 error is the error of failing to reject a null hypothesis. So there was a difference, but we weren't able to detect it because of too small of a sample, or it was the effect size was too small. It wasn't a big enough difference that we could detect it repeatedly. So it's also called a false negative. So it's when we fail to detect it. And so like if you think of different types of testing, so like if we're screening for, let's say, colon cancer, would you be more afraid of a type 1 error or a type 2 error? The fact that they told you had colon cancer when you actually didn't, okay, like the cocaine that wasn't actually cocaine, or would you be more upset if they told you you didn't have colon cancer when you actually did? And then you couldn't intervene in time due to the radiation, chemo, and stuff like that. So sometimes we want really sloppy, sensitive tests just to be careful. But sometimes, I mean, both error is not good, but sometimes one of them will clearly be more of an issue than, or depending on your perspective, which we'll get into today as well. All right, so the probability of a type 2 error is denoted as beta. So alpha is a type 1 error, beta is a type 2 error, and it depends on the effect size, which means how far off is the true proportion from the hypothesized proportion. So if we have a true null hypothesis and we reject a null, then that was no error. Ooh, wait a second. If the null is true and we reject it, yes, then that would be a type 1 error. If the null is true and we didn't reject it, then there was no error in that case. Now, if the null hypothesis was false and there actually was a difference and we rejected it, then there was no error. But if we reject it and we fail to reject it when it was false, then that would be what we call a type 2 error, which is a false negative. The power of the test is denoted as 1 minus the beta. So if we go back to here, whatever this beta value is, 1 minus that beta would tell us the power of the test. What percent of the time could we detect the difference from the effect size? Power of the test is actually pretty difficult to calculate, again, because we have to know what the true proportion is, and most of the time we don't know that. All right, example 1. A local newspaper at a large city wants to assess support for the construction of a highway bypass around the central business district to reduce downtown traffic. They survey a random sample of a lot of city residents and find that many of them support the bypass. All right, construct a 95% confidence interval to estimate the proportion of residents who support the construction of the bypass. All right, so confidence intervals, if you remember how to do that, we go to stat, arrow over to test. This is going to be a it's towards the bottom, it's beta or alpha, 1 proportion z interval. And they said that we found 542 out of 1152, and we want 95% confidence. Hit calculate, boom, go. All right, so that's our interval. I didn't type it out, but you can see right there. So we would interpret that we're 95% confidence the true proportion of city residents who support the bypass is somewhere between 44.16% and 50%, or 49.931%, however you want to do it. All right, so based on the confidence interval, test a null hypothesis that residents want to keep the business district as is. So our null is going to be that they want to keep it the same, so there's 50% or less, so that it's equal to 50%, which is that it's split. You have to have a majority for it to pass, right? So 50% residents don't want, there's not a majority support for the bypass. The alternative, we're going to be interested in seeing if there is support, which is going to be that it is more than 50%, which is that the residents do want to bypass. Now we're going to use the confidence interval to test that. Is 50% contained in our interval? No, our interval is entirely below 50%, which means with 95% confidence, we believe that there's not enough support and that it won't pass. Now, we won't know if it actually passes or not until, election day or whenever they do this. So that's kind of the whole thing. And that's how we base on confidence intervals, margin of error, and that's how we do polling and stuff like that for political polls, which is kind of cool. So what was the alpha level that we actually used on this one? So if we have a 95% confidence interval and we're doing a one-tailed upper test, so what percent is going to be on one tail of a 95% confidence interval? Well, there's 5% left on both sides. So what's left on one of the sides would be 2.5%. So we use an alpha level of 2.5%. Now, if we were doing a two-sided test, then it would just be a 5% alpha level because that's 5% error on both sides, right? What is your conclusion? Well, because it was not contained within our confidence interval, 50% was not contained in our confidence interval, we don't believe that we have enough evidence to suggest that it would pass. So we failed to reject a null hypothesis. The confidence interval suggests that less than 50% of the population want to bypass. So we don't have enough evidence to suggest there's a majority support for it. Well, what would you conclude if your confidence interval was here? All right, well, now 30% is contained in there, but it has to be entirely above it for us to say that there's enough evidence that we believe that there is support for it. So in that sense, essentially our entire confidence interval, it would have to be above it in order for it to be within the top 2.5% of our observations. So even if it was this, it would be inconclusive, which we still fail to reject a null hypothesis. The confidence interval still contains 50%. Okay, and that would still be with a 2.5% alpha level. But if our confidence interval was entirely above the 50%, then we would have enough evidence with an alpha level 2.5, because there's 2.5% on one side, that we would be able to reject the null hypothesis in favor of the alternative meaning we believe there is support, a majority support for the bypass. Last one I'm going to do with you, and we'll be able to edit some of that out, so hopefully it'll be under 30 minutes, which is my goal. Quality control. Production managers on an assembly line must monitor the output to be sure that the level of defective products remains small. They periodically inspect a random sample of the product items produced. If they find a significant increase of the proportion of items that must be rejected, they will halt the assembly process until the problem can be identified and repaired. In this context, what is a type 1 error? So a type 1 error is the same as the alpha level. It's also called a false positive. So our null hypothesis is that there's no increase in defective products. Then the alternative is that there is an increase in defective products and we need to stop production. So a type 1 error is that we stopped production when we didn't have to. There was a false positive, like a false alarm, basically. Good way of thinking about it, right? So that we rejected a true null hypothesis, so there really was no difference in the defect rate. It stayed the same, but we stopped production unnecessarily. In this context was a type 2 error. So that's a false negative, which meant that we failed to detect that there was a change and an increase in the defect rate. So that would be that we failed to reject a false null hypothesis, meaning that there was an increase in the defects, but we failed to stop production. We failed to detect it. The power of the test wasn't able to detect it. So which error would the factory owner consider more serious, and which error might a customer consider more serious? Now, on these, depending on your perspective, you might be more afraid of one of the types of error. But that doesn't mean that each person is only afraid of one type of error. We don't like either error, okay? And in fact, if we didn't have any error, that would be great, right? But that's not how the world works. There's always gray areas, right? And there's going to be errors. We just need to know what those errors are before we state our conclusions, and you should always ask your doctors if you're tested for anything, what is the false positive and the false negative rate. All right, so which type of error would the factory owner consider more serious? Now, from the factory owner's perspective, he's not going to like a type 1 error because they're unnecessarily stopping production. So if we have too sensitive of a test, where the alpha level is too sloppy, 40%, just like the Coke example, then they're constantly stopping production and checking everything, looking for defects and stuff like that, and errors in the manufacturing process, and there was nothing. False alarm, right? That's going to get really annoying. It's going to cost them a lot of money if they're constantly having to stop. So he's not going to like a type 1 error because it's a waste of money for unnecessarily stopping production. Now, is he going to like a type 2 error? Well, no, he's not like that either, because if they want to detect whenever they have problems, so that it doesn't ruin their reputation, and they have good quality control, and their customers are happy, right? So both of them are an issue, but they're primarily probably going to be worried about type 1 error because it would be unnecessarily wasting money. Which error might customers consider more seriously? Well, again, this is actually both, but they're primarily because they're the ones receiving the product. They don't want defective products. So if there's more defects going on in the manufacturing process, they're gonna want to be able to detect that, and so that they don't receive the defective product. Now, they're also not going to like a type 1 error because if they're constantly wasting money stopping production, that's going to increase the manufacturing cost, which is going to, in the end, cost more. We're going to pay more for that product. So we might want really high quality control, but we don't want to pay unnecessarily for it if they're constantly being inefficient and stopping production. Okay, so just keep in mind there's usually a perspective, and from the perspective, they probably are going to be more worried about one or the other, but doesn't mean that you can't make an argument for the other one. And on the test, you can actually make an argument for either one. Okay, so that's it. Let me know if you guys have any questions. This was a super fun one. I feel like we're really getting into the good stuff of hypothesis testing. So I'm excited to be able to lecture this one in person tomorrow on Tuesday, or in person on Friday. So I'll see you guys later. Let me know if you have any questions.